Hey everyone, I just wanted to make a video about discussion worksheet 7 because I know that some of the concepts covered in this worksheet, like moment of inertia, center of mass, and dot product and cross product, can be a little bit tricky, especially if this is the first time you've seen these kind of problems. So in this video, I'm just going to be working through each problem of this worksheet step by step while explaining my thought process behind my answers. And hopefully you'll find this video helpful and it'll clear up any confusion you might have about these concepts. So in problem 1, we have 6 different rigid objects. They're all comprised of 6 small spheres connected by massless rods of equal length, but in some of the diagrams we have shaded spheres, we have unshaded spheres, and they're all on different axes. And so we have to rank these objects based on their moment of inertia about the x-axis from greatest to least. So the important thing to know about this problem is that because our moment of inertia is about the x-axis, that means that any objects that lie on the x-axis, they're not going to have any contribution to our moment of inertia, because the moment of inertia is given by the equation I is equal to mr squared, where m is the mass of the object and r is the distance of that object away from the axis of rotation. So if our spheres lie on the x-axis, then the distance r is going to be 0, and so therefore I is also going to be 0. So all we need to do really is to look at the spheres, the masses of these spheres, for the different objects. So in object A, you can see that there are 4 unshaded spheres, and in object B there are also 4 unshaded spheres. Here we see that there are 2 shaded spheres, but because they lie on the x-axis, we don't care about them. We only care about the spheres that are on the z and y-axis. So therefore, because A and B both have 4 unshaded spheres on the z and y-axis, they're going to have the same moment of inertia. And so I'm just going to write that A is equal to B. And then for diagram C, there are 2 unshaded spheres on the z-axis and 2 shaded spheres on the y-axis. In diagram D, there's 2 shaded spheres on the z-axis and two unshaded spheres on the y-axis. And for diagram E, there are 2 shaded spheres on the y-axis and 2 unshaded spheres on the z-axis. So because in diagrams C, D, and E, they all have 2 shaded spheres and 2 unshaded spheres, they're all going to have the same moment of inertia. And so I can write that C is equal to D is equal to E. And then lastly, we have object F, which has 4 shaded spheres. And we know that the shaded spheres have more mass than the unshaded spheres, and so F is going to have the greatest moment of inertia about the x-axis. And so in terms of moment of inertia, our order from greatest to least is going to be F is greater than C, which is equal to D, which is equal to E, which is greater than A and B, which are equal to each other. So next question is, does it matter that the axis of rotation is the x-axis? Yes, it matters, because the moment of inertia is all about the distribution of these masses about the axis of rotation, and so it matters what axis you choose to be your axis of rotation. If our axis of rotation was the y or the z axis, then any spheres that lie on those axes would not count towards our moment of inertia. And then next, we are given numerical values for the masses of the shaded and unshaded spheres, and we're also told that each sphere is the same distance away from the center, and we have to calculate the moment of inertia of the system about the x-axis. And so our equation is equal to I is equal to mr squared. But here, this symbol sigma basically means that we are taking the summation of these mr squared. So we take the mr squared of each sphere and then we add all of them up to find the total moment of inertia. But in this case, all of these spheres are unshaded and they're all the same distance away from the axis. So the mr squared for each of those four spheres is going to be the same. So I can just write that our total moment of inertia I is equal to 4 MAR squared, where A is the mass of the aluminum unshaded spheres. So I'm just going to plug in my numbers, and then I'm going to get 4 times 0.1 kilograms times 0.1 meters squared. That's going to give us 4 times 10 to the negative 3 kilograms times meters squared. And then the last part of this question says, if we double the distance of each sphere from the center, would the moment of inertia increase, decrease, or stay the same? If it changes, by what factor would it change? So from the equation I equals mr squared, we can see that the moment of inertia depends on the square of the distance. So therefore, if we have our distance and we double it to be 2r and we square it, then we're going to get 4r squared, which basically means that our moment of inertia is going to increase by a factor of 4. So problem 2, we are given a long straight rod stretching from x equals 0 to x equals L along the x-axis, and we're told that it has a non-uniform mass distribution given by this lambda function such that the mass decreases along its length. So I'm just going to draw a diagram here. This is going to be my rod. I'm going to mark the left end of the rod as x equals 0, and I'm going to mark the right end of the rod as x equals L. And if the rod has a total mass of m is equal to the integral of dm, transform this integral into one in terms of dx and solve for the constant a. So we need to know, how does our quantity dm relate to dx? Well, we know that dm is equal to dm over dx times dx, right? Because I can cancel out the dx's and dm will equal dm. But dm dx is also our lambda function, our linear mass density. So I can express dm as lambda dx. And our lambda function basically tells us the amount of mass per unit length. And so now I can substitute in my expression lambda dx for dm and get that the total mass m is equal to the integral of lambda dx. And we are integrating from 0 to L because those are the ends of my rod. The left end is 0 and the right end is L, so we're integrating from 0 to L. And then now I'm just going to plug in our function for lambda, which is given to us to be a times 1 minus x over L dx. Now, I noticed that a is a constant, so I can pull it out of the integral, and I can write a times the integral from 0 to L of 1 minus x over L dx. And here, I'm just going to use the power rule. I'll write it over here on the side, which says that the integral of x to the n power is going to be equal to x to the n plus 1 power divided by n plus 1. So in this case, I'm going to get a times x minus x squared over 2l from 0 to L. And because 0 is my lower bound of integration, when I plug in 0 for x, I'm just going to get 0. And so all I need to do is kind of plug in L whenever I see x, and that is it. So I'm going to go ahead and do that. And then I'm going to get a times L squared minus, my bad, a times L minus L squared over 2L. And now these L's are going to cancel out, and I can write that as a times L minus L over 2, which further simplifies to just a times L over 2. So now we know that m is equal to a times L over 2, and it asks us to solve for the constant a. So I can just rearrange this, and then I get that a is equal to 2m over L. In part C, it asks us to calculate the center of mass of the rod as measured from the origin, and it gives us the equation for the center of mass here. It says that x, position of the center of mass, is equal to 1 over m times the integral of x dm. So I'm just going to write that here. X cm is equal to 1 over m times the integral of x dm. But remember from part B that dm is related to dx by the linear mass density function, and so I can express this integral as x times lambda dx. And then again, we're integrating from 0 to L because those are the ends of our rod. And once again, I'm going to plug in the function for lambda that is given to us. So I get 1 over m times the integral from 0 to L of x times a times the quantity of 1 minus x over L dx. And again, a is a constant, so I can pull it out. And I can write it as a times 1 over m times the integral from 0 to L of x times the quantity of 1 minus x over L dx. Now, in order to solve this integral, I need to distribute the x's into the parentheses. So I'm going to get a times 1 over m times the integral from 0 to L of x minus x squared over L dx. And again, it's just a simple power rule, so I get a times 1 over m times the quantity of x squared over 2 minus x cubed over L, 3L, from 0 to L. And because my lower bound of integration is 0, I can just plug in L for whenever I see x, and I can get a times 1 over m times L squared over 2 minus L cubed over 3L. But I can kind of cancel out the L cubed into 3L. I can get a times 1 over m times the quantity of L squared over 2 minus L squared over 3. And I can further simplify that down to a times 1 over m times L squared over 6. And the problem tells us to substitute in our expression for the constant a that we found in part A. I think it should say part B actually. But yeah, so we know that a is equal to 2m over L, so I'm just going to plug that in. So I get 2m over L times 1 over m times L squared over 6. The L's are going to cancel out, the m's are going to cancel out, and the 2 and the 6 are also going to cancel out, and we can simplify this down to L over 3. So there is our position of the center of mass from the rod as measured from the origin. In part D, do we expect the value calculated in part B to be greater than, less than, or equal to x is equal to L over 2, i.e. the center of mass of a uniform rod? This should actually be part C. So we calculated the value in part C to be L over 3, which is less than L over 2. But conceptually, we expect our value to be less than L over 2 because more of the mass is concentrated near the origin. We're told in the problem that the mass decreases along its length, and we have an uneven mass distribution, a non-uniform mass distribution. So we expect more of the mass to be concentrated near the left end of the rod, or near the origin. And then in the final part of this problem, we have to calculate the moment of inertia of the rod about the origin, and it gives us the equation that I is equal to the integral of x squared dm. Just like the previous two integrals, I am just going to plug in lambda dx for dm, and I'm going to get the integral of x squared lambda dx. And again, our bounds of integration are from 0 to L. We're given that lambda is equal to a times 1 minus x over L dx. And again, I can pull a out of the integral because it's a constant. So I get a times the integral from 0 to L of x squared times the quantity of 1 minus x over L dx. And again, I'm going to distribute my x's into the parentheses, and we're going to get a times the integral from 0 to L of x squared minus x cubed over L dx. Now I use the power rule to integrate, and I get a times the quantity of x cubed over 3 minus x to the 4th over 4L from 0 to L. And again, I just plug in L wherever I see x, and I get a times L cubed over 3 minus L to the 4th over 4L. I can simplify this further because the L's cancel out, and I can get a times L cubed over 3 minus L cubed over 4, which simplifies to a times L cubed over 12. But again, we know that a is equal to 2m over L from part B, so I can express this as 2m over L times L cubed over 12. The L's will cancel out, the 2 and the 12 will cancel out, and I can express our final answer as ml squared over 6. And then this last page of the discussion worksheet is all about vectors, namely the cross product, dot product, and the magnitude of vectors. So for A cross B, you can find the cross product by taking the determinant of a 3x3 matrix. And so our 3x3 matrix is going to look like this. Our top row is going to be our I, J, and K hat unit vectors. The second row is going to be the components of the A vector, so that's going to be 1, 2, and 3. You see that here. And then for B, it's going to be 2, 1, and negative 1. And the way you take the determinant of a 3x3 matrix in this case is you're going to have a 2x2 matrix with the I component, I hat, and then we're going to ignore the column and the row that I hat is in. So we're going to ignore the top row and the left column, and we're left with this. And so this, whatever's in the circle, is going to be my 2x2 matrix. So we're going to have 2, 3, 1, and negative 1. And then for our J component, it's going to be minus, because that is part of the definition of the cross product. It's always a minus J component. We're going to ignore the row and the column that J is in. So we're going to ignore the top row and the second column, and we're left with 1, 3, 2, and negative 1 times J hat. And then for K, it's going to be plus, and then again, we ignore the column and the row that J are in. And so we ignore the top row and the third column, the rightmost column, and we're left with 1, 2, 2, and 1 for our 2x2 matrix times K hat. And the way you take the determinant of these 2x2 matrices is, let's just say they're made of elements A, B, C, and D. Well, then the determinant is going to be A times D minus B times C. So I'm going to multiply these two numbers, and then I'm going to multiply these two numbers, and I'm going to take the difference of them. So I'm going to have 2 times -1 minus 1 times 3. And this is going to be for my I hat component. And then here I'm going to have 1 times -1 minus 2 times 3 is going to be for my j hat component. And then for k, I'm going to have 1 times 1 minus 2 times 2. That's for my k component. And now we just do the math. So then this is 2 minus 3. Oh, this is -2 minus 3 for I hat, minus 1 times -1 is -1. So that's -1 minus 6 for my j hat component. And then I'm going to have 1 times 1, that's just 1, minus 2 times 2, which is 4, so 1 minus 4 for my k hat. And then this simplifies to -5 I hat minus 7, so that's plus 7 j hat minus 3 k hat. And I can express these vectors in bracket notation and write it as -5, comma 7, comma -3. And this is our cross product of A and B. Here we're asked to find the magnitude of this cross product. That's what the vertical lines mean. It means magnitude. And so the way you calculate the magnitude is basically the Pythagorean theorem. I'm going to take each component of the vector, I'm going to square it, add it all up, and then take the square root of the sum. So we know that A cross B is equal to -5, 7, and -3. So I'm going to take each component and I'm going to square it. So I'm going to -5 squared plus 7 squared plus -3 squared. I'm adding it all up. I'm going to take the square root of the entire thing, and I get square root of 83. And then here for A dot B, this is the dot product. If you have a vector A, and it's like, I don't know, let's just say A1, comma B1, and then B is, no, this should be A. So A1, comma A2, and then we have B is equal to B1, comma B2. Our dot product A dot B is going to be equal to A1 times B1 plus A2 times B2. So in this case, we're given that A is equal to 1, 2, and 3, and that B is equal to 2, 1, and -1. And so for this dot product, it's going to be the product of the x component or the I components of these two vectors. So it's going to be 1 times 2 plus the product of the j components of these two vectors. So plus 2 times 1 plus the product of the k components of these vectors. So plus 3 times -1. And then this is just equal to 2 plus 2 minus 3. That's just 1. And here, like I said earlier, the vertical lines mean magnitude. So what we're going to do is we're going to take the magnitude of A and we're going to multiply it by the magnitude of B. And so for the magnitude of A is going to be equal to 1 squared plus 2 squared plus 3 squared, the square root of the entire sum. And then the magnitude of B is going to be 2 squared plus 1 squared plus -1 squared, and the square root of the entire sum. And we're going to multiply these two together. and we're just going to get square root of 84. For B cross C, we're again going to take the determinant of our 3x3 matrix. Our top row is always the I hat, j hat, and k hat unit vectors. Our second row is in this case, is going to be the components of the B vector, which is 2, 1, and -1. And our third row is going to be the components of our C vector, which is -5, -3, and 1. So again, I'm going to have my 2x2 matrix for my I hat component. So I am ignoring the row and the column that I is in. So I ignore the first column and the top row, and I'm left with 1, -1, -3, and 1. And it's minus j hat component, and I'm going to ignore the top row and the middle column, and I'm going to be left with 2, -1, -5, and 1. And then for k hat, it's going to be 2, 1, -5, and -3, because I am ignoring the column that k is in, and I am ignoring the row that k is in. So I am just left with these 4 numbers. And then I'm just going to take the determinant of each of these 2x2 matrices, and I'm going to get 1 times 1 minus -3 times -1, and this whole quantity is going to be for my I hat component, minus 2 times 1 minus -5 times -1 for my j hat component, plus 2 times -3 minus -5 times 1 for my k hat component. So this is going to give me, that's just 1 minus, so -3 times -1 is +3, so that's going to be 1 minus 3 for I hat. And then this is going to be 2 times 1, that's just 2, minus -5 times -1, that's +5, so it's going to be -5 for my j hat. And then for k, it's going to be 2 times -3, so that's -6, plus, minus -5 times 1, that's -5, but we're subtracting a negative, so that's actually +5, so +5 for my k hat component. And so we get -2 for our I component, -3, right, because this is -3, but we have a negative in front here, so it's going to become +3. So we're going to get +3 for my k component, and then -6 plus 5 is just -1 for my k component. So this is my vector for B cross C, and here we're just taking the magnitude of B cross C, and so we know that it is -2 plus 3 and -1. So I'm going to get -2 squared, 3 squared, and then -1 squared. I'm going to add all of these up, take the square root of the total sum, and I'm just going to get square root of 14. So yeah, that's pretty much the entirety of discussion worksheet 7. I hope this kind of cleared up any confusion or, I guess, misconceptions you might have had about these concepts. And yeah, thanks for watching.